So I wanted to record an extra video on designing counters, and then I'll go into more in Mealy machines in later parts of the video. But to start out with our counters, we're going to talk about what I'm going to call arbitrary counter design, where we design a counter which counts in any sequence we could want. And in order to do that, we're going to limit our analysis to synchronous counters, because doing arbitrary counting with asynchronous counters, which we covered briefly in Chapter 8 before focusing in on the synchronous counters, with asynchronous counters it's a lot more difficult to construct an arbitrary design. But with synchronous counters there is a straightforward process where the synchronous counter is a special case of the Moore machine, which I will do another video on later. As the next part. So as a motivating example here, I'm just made up a sequence for our counter to count in, and so it's going to go 0, 4, 6, 7, 3, 1, 0, and repeat. And as I like to do, this is a special sequence that generates a very neat final design that you will see running around from time to time. This would be a Johnson counter. But I'm not setting it up the way we usually set up a Johnson counter. But that detail is not relevant. We are just going to treat it as though, for whatever reason, this is the sequence we want to do. And to make this work, we're first going to need to draw a state diagram, but I would like to start this out by going over the sort of the basis of what we're trying to do here. So our goal is to generate a counter which counts in this arbitrary sequence. And in order to do that, we are going to... Okay, no. That's not what I want. I want... There we go. Okay. So in order to do that, I would like... I want to describe what the pieces are going to be. So there are two important parts to this counter. We're going to need some memory, and so the job of the memory is to remember what the count is why we need memory. And so to do our memory, we are going to build this out of flip-flops. In this case, so in general, you may not build it out of flip-flops, but that's what we're going to do. And so because of the flip-flops, because of the size of these numbers, they're between 0 and 7. The numbers 0 through 7 are going to be writable using 3 flip-flops, because we only need 3 digits. The largest number is 7, which would be 1, 1, 1. So 3 flip-flops. And so if we design this using flip-flops, this is our memory block. And if we use 3 flip-flops, there are going to be 3 outputs. So, or 3 important outputs here in our counter, which, if there are 3 flip-flops, the outputs of those flip-flops will be Q2, Q1, and Q0, which is nice. So these are the flip-flop outputs for the flip-flops we're designing here. Okay, and so we're going to use this portion a little bit later, but I actually need a little bit more space, so let's move that over. So this memory is going to remember what the count is, and so the value of the count is going to be visible on these Q outputs. So Q2, Q1, Q0, read in that order together, is going to be readable as a number, either 0, 4, 6, 7, 3, 1, or 0 in this case, though in general it could display any number between 0 and 7. But in order to make the memory do what we need it to, we're also going to need inputs. And so we're going to have several inputs here, and in general you may have a different number of flip-flops, but we're going to need J, K, D, T, depending on what type of flip-flop. So there's going to be J, K, D, and T, and because there are 3 flip-flops here, there's going to be a 2, a 1, and a 0 for subscript for each of these. So depending on if we do JKs, we'll have a J2, K2, J1, K1, J0, and K0. If we do D flip-flops, we'll have a D2, a D1, and a D0. We may not, I may use this video again, so we may or may not have discussed T flip-flops. When I'm recording this, we didn't go over T flip-flops. But if we were using T flip-flops, you'd have a T2, a T1, and a T0. And so as a result of that, we're going to have at least 3 inputs, and then depending on if it's JK, we'll actually need a total of 6 inputs, but right. So we'll have these, and I'm just going to box them up, and we're going to have this input over here, and then we'll kind of just connect these guys up. And we'll just imagine that it's one output, so just for the purposes of drawing our picture. So I'm just going to fold this, and let's change the color on that, and change the color on this one as well. Yeah. So I'm just packaging these up into a single, almost like a bus, just for our image purpose here. And so the goal here is we have this memory, it has inputs, and then there's also going to be the clock. So let's throw the clock on here as well. Okay, so the clock is going to come in, it's just going to be a clock. And so our memory will remember where the count is, but we need to use the JKDT to control where the count is. So every time in this counter, the memory will tell us where we are in the count, and then we need something to sit here and tell the counter how to change its values. And the only way to do that is through this JK, D, and T. And so as a result, get the eraser there. So we need something to control this J, K, D, and T. And so that is why we have a separate box here. And so we have this other box. Actually, I don't really need to box these up. I should let them all go. No, that's fine. Okay, and then over here, so the thing which will control the memory is going to be our, so we need combinational logic here. And so it's going to require some combinational logic, and I did a good job with this box here. So let's try that again. No. Select. Okay. Try the box one more time. There, that's better. Okay, so then, yeah, that won't work. One more time. Okay, we're going to need our combinational logic. So the combinational logic, this is what we're going to design. And the job of the combinational logic is the outputs to the system. The outputs of the memory are going to run over here. Okay. So the Q values are what are going to come in here. So over here we're going to have Q2, Q1, Q0 in this case. And then, so those are going to come back. In general, there may be some control inputs, theoretically. So this is where the control inputs may come in from, but in this case we won't have any. So there's no control in this time, but in general there might be, and it would go into the combinational logic over here. But sometimes we might have a control line, let's say it was an up-down counter, then you may have a control line, you would need a control line whose job is to indicate, are we counting up or are we counting down? And so that would factor into the combinational logic to control the J, K, D, and T differently. So Q2, Q1, and Q0 go in, and then at the output, we would need, we need to control our J, K, D, T. Will be the outputs of the combinational logic. So the memory's inputs, because the memory is made of flip-flops, the memory inputs are the J's, K's, D's, T's, etc. The outputs of the memory, which are going to tell us the count, are the Q values. But in order to control these J, K, D, and T, the combinational portion outputs J, K, D, and T and accepts Q2, Q1, and Q0 as inputs. So that is so that's the block diagram, and so I'm going to end this video here, and then I'm going to continue with this particular example.